fact that she went to school to tell you that when she likes to skip.
I know. Isn't that funny? I know. She was great. All right. I still remember her name, too. This is being recorded, so I'm not going to say it. All right. So this is section 4.2. I can apply the mean value theorem. We've already discussed the warm-up. If my average velocity is 60, does this mean somewhere my instantaneous velocity has to be 60? The answer is yes, and we're about to see why. But before we see why, we're going to learn about Rolles' theorem. So before the MVT, before our final theorem, there was Rolles. So help me with, who takes French? Can you say that name? Is it Michael, Michelle? How do you say that in French?
I don't know.
I think it's
Michel. Michel?
Yeah.
Should I say it right?
Yeah.
Okay. Michel Rolles.
I don't know about the role, but
Okay.
I used to watch this TV show where the French guy was named
Michel. Michel Rolles. I said Michel Rolles. All right. So, anyway. All right. French mathematician. He was the first one to come up with this concept. It was published in 1691. This came first, and then other mathematicians read this, investigated it further, and then created the mean value theorem. This is actually just a special case of the mean value theorem. So because of it, the College Board never ever uses Rolles' theorem by name. They call everything MVT. They never call anything Rolles. However, they recognize it, and if you use Rolles to justify a Rolles theorem problem, it's fine. It's absolutely fine. It's in every single calculus textbook. So tons of people write Rolles, and that's okay. Just know that the College Board will never use the word Rolles for a Rolles theorem problem. They'll always call it MVT. So, but we're going to call it Rolles because he was the first one to come up with it. And even though it's just one specific case, it tends to show up a lot. So it's good. It's good to know to focus on this one case, and then we'll expand it to MVT in a few minutes. So Rolles' theorem has three conditions. So the first condition is the same condition that is required for every theorem you've learned this year, which is the function has to be what? Continuous, right? So get used to writing it, because every time you use a theorem, you have to write that the function is continuous. And get in the good habit of writing continuous on the closed interval a to b. I want you to develop good math habits. And one of them is whenever we're using IVT, EVT, MVT, or Rolles, all four of them deal with closed intervals. So because of that, it's good to say the function is continuous on the closed interval. Then the next requirement for Rolles is that the function has to be differentiable on the open interval from a to b. You can't be differentiable at an endpoint, so you'll never be differentiable on a closed interval. Unless that I guess I could make an exception. Unless that closed interval is within an open interval that the function is differentiable on, and you just want to focus in. But you'll always just say differentiable on the open. And then the third requirement for Rolles' theorem is that the endpoints have to have the same y values. So continuous, differentiable, and the endpoints have the same y values. Differentiable means no sharp turns, no vertical tangents. So continuous means connected. So what you end up with is if you have a smooth connected curve, that connects two endpoints, and those endpoints have the same y values, the result of the theorem is that there has to be at least one spot in between the endpoints, not at the endpoints, in between, where the slope is 0. So where the derivative is 0. All right, so what does this look like? So if I have a curve and I get from A to B, and my y value at A and my y value at B are the same, and the curve is smooth and connected, then there has to be at least one spot on the curve where the slope is 0. Now there can be more than one, right? If I have, this curve, right? As long as, pretend those are the same y values. So as long as my endpoints have the same y values, there has to be at least one spot where the slope is 0. There can be more. but there has to be at least one. Does that make sense? That's what Rolles' theorem says. Okay, so let's go. We're going to do a couple practice problems with Rolles, and then we'll move on to MVT. Everyone have this stuff written down? You showing you need another minute? You got it? All right, so we're going to do some simple examples. So first, determine if Rolles' theorem can be applied to f of x equals x squared minus 3x on the interval from 1 to 2. If so, find the value of c such that the derivative equals 0. So the first thing we have to do is decide if Rolles can be applied. What is the first thing we have to check? Continuous. Is this function continuous?
Yes.
Yes. Do I have to prove that it's continuous?
No.
No. I just have to state that it's continuous. So the first thing you're always going to write for every theorem is that f of x is continuous on, in this case, the interval from 1 to 2. Check. What's the next thing you have to check for with Rolles? Differentiable. How do you know if a function is differentiable? You differentiate it. Very good, Brian. All right. Yes, absolutely. So you have to find the derivative. Everyone take a second and find f prime. All right, what's f prime? Are there any x values that would cause a problem with the derivative? Any time where the derivative is not continuous?
No.
No, derivative is always continuous, then the function is always differentiable. So it's kind of like when you're checking for continuity, you check for continuity on the original function. When you're checking for differentiability, it's kind of like you're checking for continuity on the derivative. So anyway, here we go. So f of x, go back to blue. F of x is differentiable on the open interval. Check. What's the last thing we have to check for with Rolles' theorem? We have to check the y values at the endpoints, right? So everyone go ahead and take a second and find f of 1 and f of 2. Wait 2 more minutes. Stay for the end of Rolles. Okay. Alec, what'd you get?
I got -2.
For both of them?
Yep.
Ooh, that means that our third check works. So we'd write f of 1 equals f of 2. Check. Check, check, check. 3 checks, Rolles' theorem applies. So we'd say, therefore, Rolles applies. All right, we don't have to write a conclusion statement. They didn't ask for you to explain why. What they asked for you to do is to find the value of c such that f prime of c equals 0. So in order to find that c, what you're really doing is setting your derivative equal to 0 and solving for x, because c is really an x value. So for this next part, what's our derivative? 2x minus 3. So for this next part, you set your 2x minus 3 equal to 0. All right, Kirtana, how are you? Are you? You look a little chilly. You're fine? Okay. What do you get when you solve this for x? 3 halves. Beautiful. Is 3 halves in our open interval between 1 and 2? Yes, it is. I always have students who do the math wrong, and so they'll set the derivative equal to 0. They'll solve, and they'll get something like x equals 7 halves or something like that, and they'll go, oh, 7 halves isn't in the interval, therefore there is no value of c, right? Except if you said that Rolles applies, there has to be a value of c. That's why it's a theorem, right? It's been proven it has to be true. So if you say it applies and then you don't find a C, you've either disproven Rolles' theorem, right? And then we need to publish your work, or you've made a mistake somewhere, right? So you got to find a C. There has to be a C. So our C in this case is 3/2. And just so you know, C has to be in the open interval. It can't be at an endpoint. No endpoints. So Rolles' theorem, it proves that there has to be a C inside of the endpoints, not at the endpoints. Okay, not so bad, right? Ready to try another one? With words? Dun, dun, dun. All right, because you know on your test you're not going to get just an easy little show that Rolles' theorem applies. We're going to give you words, right? Okay, so let's do some with words. Suppose that f of x is a differentiable function with selected values shown below. By the way, the College Board loves to use tables for their theorem questions. They love tables. So, explain why f of x must have at least 2 horizontal tangents. What I'd like you to do is take a minute or two, look closely at the table, discuss this with your groups, see if you can come up with proper proof as to why there have to be 2 horizontal tangents on the function of f of x. All right, I'm going to turn off the recorder and let you guys.
One that was also continuous. And so based on that, Rolles' theorem applies to both of them, so therefore there must be an FC equals 0, which basically the horizontal tangent.
Beautiful. That was perfectly put, right? I wish I'd recorded the whole thing. So, all right, I'm going to recap for the recording. So what Jennifer just said was, because f of x is differentiable, every differentiable function has to be what? Continuous. It's the first requirement for differentiability. So if f of x is differentiable, it has to be continuous. And if you're worried about how you write it, I will tell you historically what the College Board will, the way that they will word this. If you just write f of x is continuous on the close, f of x is differentiable on the open, that's fine. But I will tell you historically, traditionally, what we, hang on, moving this back. Okay, so f of x is differentiable and therefore continuous on, now they didn't give an interval, they just said differentiable, right? So whether you give an interval or not, it's kind of a judgment call here. I personally would go ahead and just say on, let's just do the open interval 1 to 20, because it's really, if they just say it's differentiable, it means it's differentiable everywhere. Now, the people in first period were asking, do we have to write those intervals? The College Board, if the function really is continuous and differentiable everywhere for all real numbers, and you just write f of x is continuous and differentiable, they accept that as long as it's true, right? But if it's not true, if f of x is only continuous or differentiable on an interval, and you just say it's continuous and differentiable, you're implying that it's like that everywhere, and you're lying. So then you have to put the interval. I personally am very picky. I want you to put an interval. But the College Board, as long as you're acknowledging continuity and differentiability and what you're saying is true, they accept it. Okay. So anyway, all right. So we are differentiable and therefore continuous. I'm putting on the open interval from 1 to 20. Really, it's everywhere. Okay, so we've got the first 2 requirements of Rolles. And then what Jennifer said was she used the interval from 3 to 8. Why did she pick 3 and 8? Same y values, right? So f of 3 equals 5, which equals f of 8. Check. And f of, what's the other one? 9 to 15, right? F of 9 equals 2, which equals f of 15. Check. So therefore, here, now they didn't ask us to find C, and we couldn't find it. There's no way to prove like which x value actually has a slope of 0. So really all you're doing now is writing your conclusion statement for your theorem. So explain why f must have at least 2 horizontal tangents. Well, you've just proven right here that Rolles' theorem applies on 2 separate intervals. So there must be 2 separate instances where the derivative is 0, which means where the slope is 0, which means we have a horizontal tangent. All right, so how do we write that? We write, therefore, by Rolles' theorem, and then you just rewrite your problem. F of x, you just restate the problem as a statement. F of x must have at least 2 horizontal tangents. Yes. Sorry, you're late. You could have gone. I'm sorry. I've just realized. Okay. All right. Okay. Okay. So, any questions on that? So, whenever you have a question and it's asking you, does the slope have to equal 0 somewhere in this interval? Look for y values that are the same, because then you can use Rolles' theorem and it's really easy. If you don't have any y values the same, someone in first period justified this not with Rolles' theorem, and what they said was, they said, well, if you look at the data is increasing and then decreasing and then increasing, and if you have a differentiable function that increases and then decreases and then increases, you have 2 direction changes. Since it's differentiable, it's got to be smooth, which means there must be 2 horizontal tangents minimum, right? That works for justifying, but you got to be so careful how you do it, because if you state something wrong, you lose the points. And I'm going to tell you right now, I'm just going to give you an example. Hear this on the recording. If I were to say f of x is increasing from 1 to 6, that would be a big fat lie. Because I don't know what's happening at 2, right? At 2, the y value could be 97, right? We have no idea what's going on in between. So you never, ever can make a statement about a table that assumes values you don't know, right? I can't say f of x is increasing from x equals 1 to x equals 6. What I can say is f of x is increasing somewhere in the interval from 1 to 6. Somewhere in there, it's got to increase, right? There's no other way to get from -3 to 8 without going up, right, on a differentiable function. And then somewhere in the interval from 6 to 12, it's got to decrease. And somewhere in the interval from 12 to 20, it's got to increase, right? So as long as you're kind of vague with your description, vague but correct, then they accept it. But if you make statements about tables that assume y values that you don't know, you lose your points. So you got to be careful with that. That's why Rolles' theorem is better, because if you have 2 y values that are the same, you're just done. Rolles' theorem, easy, done. All right, moving on. MVT. Our main use of Rolles' theorem is proving the following important theorem, which was first stated by another French mathematician, so Joseph Louis Lagrange. You are going to learn to love and hate Lagrange as time goes on. Just remember the name Lagrange when you get to series at the end of the year and you have to learn the Lagrange error found theorem. It's a fun one. I actually don't mind it. I kind of like Lagrange. In Calc 3 on Friday, we're doing Lagrange multipliers, which is a way of finding extrema on a function. Lagrange was a busy mathematician. So MVT is great. So if you like MVT, learn to like Lagrange. Just remember at the end of the year when you learn the Lagrange error bound theorem that, okay, but he's not so bad. He gave us MVT. All right, here we go. The mean value theorem. Let f be a function that is continuous on the closed and differentiable on the open, and that's all that's required. So any function that is continuous and differentiable. So if you have a function that's continuous and differentiable, then here's our results, our conclusion. then there is some number inside the open interval where the derivative equals this thing right here. What is f of b minus f of a over b minus a? What is it? It's slope, right? This is your slope of the secant. This is your average rate of change, right? So what it's saying is somewhere inside of the interval, the instantaneous rate of change has to equal the average rate of change. It's the only way to get from A to B on a continuous function, a continuous and differentiable function. So if I get, so there's a lovely picture here from your book. So if this is point A and this is point B, the slope of the secant, that's the slope of the line that connects the endpoints. As long as the curve is continuous and smooth, right? So continuous and differentiable, so smooth and connected. As long as the curve, the actual function, is smooth and connected, there must be at least one place inside the interval where the slope of the tangent is the same as the slope of the secant line. All right, so how is Rolles just a special case of MVT? Because in Rolles, if you do the slope of the secant, what is the slope of the secant when the y values are the same?
0.
It's always 0, right? If your y values are the same, then the change in y is 0, and therefore your slope is 0, and therefore there must be at least one place in the interval where the slope is 0, right? So Rolles is actually just a special case of mean value. You can use MVT for every one of these problems, including the Rolles. You never have to use the word Rolles. You can always just say MVT, and you'll be fine, because it's just another special case of MVT. So anyway. All right, so does everyone have this down? 2 conditions and the result? Okey-doke. Little practice. So first simple practice problem. Determine if MVT can be applied to f of x equals 2x cubed plus x plus 4 on the interval from -2 to 1. If so, find the value of c based on the theorem. What's the first thing you have to check? Continuous. Is this function continuous?
Yes.
Yes, it is. Why? How do you know? It's a polynomial. Polynomials are always continuous and differentiable. Why are they continuous and differentiable? Because they have no denominators and no roots, right? So f of x is continuous on -2 to 1. Check. All right, how do we know for sure it's differentiable? What should we do? Differentiate it. Lucas, what's the derivative? 6x squared plus 1. Very good. Is that derivative ever undefined? No. Then the function is different. All right, so f of x is differentiable on open, -2 to 1. Check. 2 checks. That's all you need for MVT to apply. So this one doesn't have you explain anything, so you can write just therefore MVT applies. Now we have to find C. C is the x value where the slope of the tangent is equal to the slope of the secant. Or in other words, where the derivative value is equal to the slope of the secant. We have our derivative. Do we know what we need to set the derivative equal to? No. So what are we going to have to find? Slope of the secant. We're going to have to find our AROC. So I'm going to put to find C. First thing you're going to have to do is find your average rate of change or your slope of secant. All right, so average rate of change. F of 1 minus F of -2 over 1 minus -2. This just never goes away. Keeps popping up. So take a minute. Oh, I'll put the function so you can see it. There we go. So there's a function. Take a minute. Find the average rate of change. Emma, you are so fast.
Oh.
People are still writing down the problem. Emma's like done with the whole thing.
Isn't it minus?
Well, it is minus. So 14
Oh,
is
minus.
negative.
God.
Positive.
Yeah, gotta watch the negatives.
I know I see 12 on. I'm like, okay, I'll figure it out sooner than later. The recording's going. The recording.
Oh, well, that's okay. Let's go and get moving. Okay, so let's see. Hi, Mahika. How are you? Good. What'd you get for F of 1? Close.
7.
7. Good. Minus. Did you get F of -2?
Oh, I could do
-14. Very good. You're absolutely right. All right. Over what's 1 minus -2? What is it? 3. Guys, be so careful with your negatives, right? Be so careful. 7 minus -14 is 7 plus 14, or 21/3, or what I like to call 7. Okay. All right. So that's our average rate of change. What are we going to do with it? We're going to set our derivative equal to it and solve. So 6x squared plus 1 equals 7. All right. Emma, when you solve this, what do you get?
You get plus or minus 1.
You get plus or minus 1. Does that mean that that there are two C's, positive and -1? Not necessarily. Let's look at our interval. Why, I don't know how to say that. Why can't 1 be one of the C's? Because it's at the end point. You have to be in the interior of the interval. That's the basis of the theorem. So the only one that is the answer is -1. You can have multiple C's, but they have to be in the interior of your interval. They can't be at the end point. Okay, so that is that. You ready to try one with words? Oh, yeah, sorry.
So what's C?
C is, here, I'm going to show you, is it okay if I show you in the picture?
Yeah.
Okay, so C, so you have some function, right, start to end. You have a secant line that connects the endpoints to find the slope of the secant. That's your AROC, right? So there is some spot in the inside of this interval where the slope of the tangent is the same. C is the x value where your function has the same slope, instantaneous slope, as it does average slope. Okay, so C is an x value where the derivative is the number that you're looking for. Okay. All right. Words. Here we go. A swimming pool is being filled with a hose. A differentiable function w of t represents the number of gallons of water in the pool at time t. Various values of w of t are indicated in the table below. Part A. Explain why there must be at least one time on the open interval from 0 to 240 when the pool was filling at a rate of 3 gallons per minute. Part B. Explain why there must be at least one time in the open interval from 60 to 120 when there were 200 gallons of water in the pool. Two different explanations, two different theorems, they might not both be theorems we talked about today. So here's what I want you to do. I want you to take a few minutes first, work this out on paper, discuss with your groups, and then I want full answers on whiteboards as though I were grading this for a test, okay? So take a few minutes, discuss it in your seats first, then work out, I want to see the answers on your whiteboard. I'll say it again. Well done. Okay. So part A, when you have to prove that, when you're dealing with rates, when you want a rate to equal something, that's MVT. When you want a Y value to show that a Y value has to be something, that's IVT. And I'm going to summarize. The next screen is us kind of summarizing the 4 theorems that we've learned, because any theorem is fair game to be on your next test. So just know, even if it's not something you learned in this unit, doesn't mean that it's not going to show up, right? Okay. So for part A, since we're talking about rates, it's MVT. I was very pleased at how many of you wrote differentiable and therefore continuous. I think I just did continuous, differentiable, check, but that's totally fine. So there is a problem with some of the boards though. Some of you would not have gotten full credit. So most of you would have, but some of you did not. So here's why. Just because a function is continuous and differentiable does not mean there has to be a place where the derivative is 3. It means the MVT applies. So how do you prove that the derivative has to actually be 3? What do you need to show to justify that there's got to be a place where the derivative is actually 3? Yeah, Casper.
The average rate of change equals the derivative.
You've got to find the average rate of change, and you have to have it written down. So continuous and differentiable just shows that MVT applies, but the conclusion of MVT isn't that the slope equals 3. The conclusion is that the slope equals the average rate of change. So you've got to find the average rate of change. So the average rate of change in this problem is 3, but somewhere on your paper you need to write it, right? So you find the average rate of change. It happens to be 3. Yay! Therefore, and then you write your conclusion statement. Therefore, and whenever I write my conclusion statement, I always start with therefore by the insert theorem here, and then I just rewrite the problem as a sentence. Therefore, by the MVT, there must be at least one time in the interval 0 to 240 when the pool was filling at a rate of 3 gallons per minute. And I never go outside of that. I just restate the problem, and that makes me happy. So that's all you have to do. So continuous differentiable, that shows MVT applies, but in order to show that it was actually 3, you did have to show that you found the average rate of change. All right. Part B, how do we know that there has to be at some point where W of T is 200, where the the water in gallons, how do I say this? The amount of water in the pool is 200 gallons. Okay, so how do I show that? That's IVT, which all of you figured out, so very, very well done. IVT deals with function values, Y values. MVT is rates, IVT is Y values. So if you're asked about, does some Y value have to exist between 2 other Y values? That's an IVT question. IVT, you have 2 checks only. The first check is that the function has to be continuous. So continuous. And then the second, we didn't know derivatives when we learned IVT. We learned IVT in chapter 2. So there's no differentiable in IVT. If you say it, it's fine because it's true, but you don't have to say it. The only thing you have to show for IVT is that the number you want, which is 200, falls in between the Y values of the endpoints of your interval, which it does, right? So you had to show that, so I wrote over here what my Y values were. W of 60 is 140, W of 120 is 320, therefore W of 60 is less than or equal to 200, which is less than or equal to 120. If you don't have the equals, that's okay. IVT, you can actually be at an endpoint. IVT is okay at endpoints, but it's fine because it's in the interior here, so it doesn't matter. So anyway, so whether you have less than or equals is fine, and then write your conclusion again, just restating the problem. Therefore, by the IVT, there must, I wrote be at, but I accidentally connected them, so it's beat. So there must be at least one time in the interval 60 to 120 when there were 200 gallons of water. So you're just rewriting the problem, which I think every single one of you guys got. So well done on your IVT. Yeah, good job. Okay. Any questions on theorems? Yeah, Nidhi.
I was just going to ask for the College Board, will they understand when you write MVT?
Yeah. As a matter of fact, if you look at the scoring guidelines for College Board questions, they abbreviate IVT, MVT, EVT. They always just use the 3 letters. I personally, if I were taking an AP exam, I don't abbreviate anything because I don't want to take any chances. And you actually, even though it feels like you have to write a lot in this class, on the AP exam, you're only doing one of these, right? There'll only be one. So you'll only have to write it once. So you might as well just write it out and be safe, right? So I always say never abbreviate on the AP exam. But when I'm doing my own work, I abbreviate like crazy because we have to do so many of them, right? Okay. All right. Now, this last little thing, you don't have to write. You can if you want to. In first period, I thought it would be good to do a little recap of the theorems that we've learned. It's not anything amazing. I'm going to put a little shade up so we can do them one at a time. So here is, if I invite you into the scary thing that is my brain, here is how I remember theorems. I remember theorems alphabetically. I know that's really weird, but that's how I remember them. I remember them EVT, IVT, MVT, Rolles, alphabetically. And the reason I like to know them in my brain alphabetically is because the number of conditions that you have to check increases alphabetically. So it kind of helps me remember what do I have to check off for each theorem. So my first theorem alphabetically is EVT. The only condition is that the function has to be continuous, and the result is that the function has a max and min on the interval, the closed interval. I'm not giving you all the fancy words, right? This is just a recap. So for me, EVT, one condition, continuous. Every single one of these has continuous, right? So one condition, continuous. The result is that the function has a max and a min. The second theorem, IVT, has 2 conditions, continuous, and the y value has to be in between the endpoints. And then the result is the y value is in between the endpoints, right? So you've just proven that the y value that y value has to exist in between the endpoints. So IVT is about showing function values. So whatever, if you're ever asked, does this function have to hit a value of this? That's an IVT question. So then you come to MVT, which also just has 2 conditions, continuous and differentiable. And MVT, the result is that your instantaneous rate of change has to equal the average rate of change on the interval, somewhere in there. So MVT deals with rates. So if you're asked about the derivative or the rate of change of a function having to equal some value, that's MVT. And then the last one is Rolles, and Rolles is the highest alphabetically, and it has 3 conditions: continuous, differentiable, y values at the endpoints are the same, and then the conclusion is that the slope has to equal 0 somewhere in the interval. If you never learn Rolles and just learn EVT, IVT, MVT, you're fine. You'd be covered. It's just that you get asked stuff about, like, where does there have to be a place where the derivative is 0? You get asked that quite a bit on the AP exam. It comes up, I'm going to say, at least maybe once in every 5 years, which doesn't sound like a lot, but that's a lot. So anyway, since it gets asked so often, it's handy. It comes in handy. If you don't know it and you just do MVT, you'll be fine. But it's nice to have Rolles in your back pocket. So that's my theorem recap. Those are the only theorems that you are responsible for being able to write the conditions and write the conclusion. You will learn other theorems, but these are the ones. These are the biggies. These are the Mac Daddies. All right, everyone kind of comfortable with this? All right, good. So today, can we do MVT? Can we do Rolles? Yes, we can. I'm going to answer for you. Yes. Okay. So I'm going to stop the recording, and now, Catherine. So this is Catherine Okikiolu, born in 1965 in England. Her father, George, was Nigerian, moved to England to study mathematics, where he met her mother, who was studying physics. Her father is the most published black mathematician ever in history. Catherine earned her bachelor's from Cambridge, her PhD from UCLA. While at UCLA, she proved her abilities by solving a problem involving asymptotics of determinants of Toeplitz operators on the sphere, as well as a conjecture of Peter Jones characterizing subsets of rectifiable curves in Euclidean n-space. Not only was Catherine the first black mathematician to earn the Sloan Research Fellowship, she was also awarded a Presidential Early Career Award for Scientists and Engineers, which was $500,000, for both her mathematical research and her development of a math curriculum for inner-city school children. She created a method for teaching negative numbers using money and debt, and is working on extending the lessons to a large number, say for 30 seconds, of real-world applications in order to teach simple math concepts. She has taught at Princeton, MIT, UC San Diego, and she is currently at Johns Hopkins. So anyone who attends Johns Hopkins, you can look up Catherine Okikiolu because she's still there. She's been studying drums, has been researching the spectral determinant, which is the number obtained by multiplying all the individual sound pitches. It's been done for 2 dimensions. She is doing it for 3 dimensions. And one last thing, her work in elliptical differential operators is considered a major contribution going well beyond what experts had considered feasible in the current state of knowledge. She is also the first black female to publish an article in the Annals of Mathematics, and it was called Critical Metrics for the Determinant of the Laplacian in Odd Dimensions. All right, guys, have a great day.
Thank you.